Hi everybody, it's my pleasure to welcome Professor Alexandra Pope to University of Kansas. Alex is a professor at the University of Massachusetts Amherst, and she did her PhD at the University of British Columbia and followed it up with a Spitzer Fellowship, so it's a prestigious postdoctoral fellowship at the National Optical Astronomy Observatory in Tucson, where we overlapped for about 6 months. She then moved to her faculty job at UMass, where she's been since 2010. And Alex is kind of really a world authority in understanding the obscure dark side of galaxy formation, the side that we don't get to see because galaxies are often obscured by dust. And she's going to talk a lot about that today. Over her career, she's really made amazing contributions, both with space-based instruments, so satellites that are launched above the Earth's atmosphere to see the light that we can't see from Earth, but also with the next generation of really large millimeter wavelength telescopes on Earth itself. So we're going to hear, I hope, some really interesting stuff about old results and new results and everything. So it's really my pleasure to welcome her here.
Thank you. Thanks, Greg, and thank you to everyone for coming to my talk today. I've had a very enjoyable day meeting with many of you. I was saying I'm in just an astronomy department back home, and so I always enjoy visiting physics departments to hear more broadly about what's going on in physics. I did my PhD in a physics institution, so it's nice to kind of reconnect with some roots there. As a caveat, like many astronomy talks you may have heard, we have a lot of acronyms and jargon that we try hard not to get into. So please interrupt me if I get, if I start using some of that jargon and lose you somewhere. That's, I don't mind that at all. So as Greg said, I'm going to talk about galaxy formation and evolution and the obscured side, so the light that's getting absorbed by the gas and dust that is prevalent throughout galaxies and re-radiated in the infrared. And one of the telescopes that's started to be really important for this, but really will take off in the next couple of years, is this large millimeter telescope down in Mexico that the Department of UMass Amherst is part owners in. So we have facility access to it, so we can do large programs with it. So I like to start my talks with this picture because this is familiar to many people when they're thinking about the formation and evolution of galaxies. So this is one of the pictures from the Hubble Space Telescope, really just demonstrating the huge variety of galaxies that exist in our universe. We're looking at 10 billion years of cosmic time in this image. We're looking at galaxies very nearby, and we're looking at galaxies whose light has been traveling to us for much of the age of the universe. This is an optical image, so the colors are representing different wavelengths of light throughout the optical and near-infrared part of the spectrum. So you can see galaxies have a wide variety of colors, wide variety of shapes. There's a lot of things happening in an image like this. So one of the big questions that we try to answer is what sets this sort of diversity of galaxies in our universe, and how do they evolve over cosmic time? Ultimately, we want to understand where our galaxy, the Milky Way that we live in, came to be and what has fueled its growth of stars over cosmic time. But this is only telling us half the story in terms of the buildup of stars and supermassive black holes in galaxies. And the most fundamental observation that demonstrates that is this observation here, which is showing the total light coming towards us as a function of wavelength from everything in the universe. So you just integrate all the light coming towards you from everything in the universe, stars forming in galaxies, black holes rapidly accreting, everything that's happening at all redshifts gets integrated down, and you look at it as a function of wavelength here. And we can see the cosmic microwave background, which we know is sort of the relic of the early universe. But everything in terms of galaxy formation and evolution is wrapped up into these two distributions here, the cosmic optical background and the cosmic infrared background. And a striking observation from this plot is that the power in the optical and the infrared is roughly equal. So half of the photons that get emitted from new stars shining or a black hole rapidly accreting material get absorbed by dust and re-radiated in the infrared. So this is showing the integrated over sort of all galaxies along our line of sight. We can take the same kind of a plot where we're looking at power as a function of wavelength and see what it looks like for some individual galaxies. So here I'm showing what we call spectral energy distribution, so just amount of power of light as a function of wavelength, and I'm showing a bunch of different types of galaxies here. The galaxy at the bottom in green is an elliptical galaxy. It's kind of lost in here, but its infrared peak is way down here. So this is, again, this is the optical UV part of the spectrum. So this is showing the unobscured light, the photons that directly reach us from stars shining. And then the infrared, which is the obscured. So that's the stuff that's been absorbed by the dust and re-radiated in the infrared. So this infrared light is probing the same star formation that's happening in the UV, but it just gets reprocessed through the dust. There's an additional step. So you can see elliptical galaxies in green don't have a lot of infrared relative to their optical. But as you look at a disk galaxy like M101, so a sort of fairly slow star-forming galaxy, or a more highly star-forming galaxy like the red one here, M82, all the way to the blue one at the top, which is an ultraluminous infrared galaxy. So this is a galaxy whose infrared is far exceeding its optical output. 99% of the photons are coming out in the infrared relative to the optical. And so you can see that there's a variety of contributions from the infrared and the optical, but for most galaxies that are forming stars, a lot of the light gets wrapped up in the infrared. So if you want to study the process of star formation, then you need the infrared to help complete the census. So just to sort of make sure we're all on the same page again, so we know that light takes time to travel. So when we look at an image like this, I told you we're looking at galaxies over much of the age of the universe. And so if light takes time to travel, we're seeing these galaxies as they were in the past. And so by making observations in a deep field like this, and determining the distances to the galaxies, we can place them at different epochs and see how they change over cosmic time. So this is just a little press release from the Hubble Space Telescope, just kind of demonstrating, different slices of the universe as you look back in time to sort of the earliest galaxies forming a few hundreds of million years after the Big Bang to sort of the early universe cosmology over here. So this is sort of showing you a little bit of the idea of what's happening. Galaxies are getting a little bit smaller as you go back in time. But let's break that down a little bit. So there's going to be sort of two fundamental quantities that I'm going to relate for you and show you on a plot here that are related to how galaxies grow. Galaxies are made of a lot of pieces. So they're made of stars, but they're also made of dark matter. They're made of gas and dust in the interstellar medium, and they're made of a supermassive black hole at the center. So today I'm going to focus on the formation of stars. And so you've got your current stellar mass, which is the amount of mass that's locked up in stars currently in the galaxy. And then you've got the star formation rate for that galaxy. How fast is it turning its current gas into new stars? So those two fundamental quantities help you determine sort of the evolutionary state that a galaxy is in. And one of the big results from the past, I guess, decade now is that there's quite a tight correlation between these two quantities at a given epoch. Okay, so you take a slice of the universe and you plot the average, average relationship between the average star formation rate and stellar mass, and you see a fairly tight relation. So each of these panels is showing a different epoch in the universe, a different redshift. So, redshift 1 is roughly half the age of the universe. So going back, 6-ish billion years, and then beyond that, 8 billion years. So looking at galaxies at different epochs. So you see at all the epochs that we've studied out to a redshift of 2.5, we see this fairly tight trend. And when you overplot the average relationship here for the different redshifts, you see that the trend is evolving as we look back towards the past, such that a galaxy of a given stellar mass, so a galaxy of a given amount of stars, as you go to more and more distant times in the universe, or as you look back in the past, that galaxy was forming stars at a higher rate. Okay, so something was allowing the gas to turn the star. So there was either more gas available, or the gas was more efficient at turning gas into stars. Okay, so this is a very fundamental relationship for sort of tracking the evolution of galaxies. I want to point out two things. I want to point out that the sort of really good statistical studies stop around, redshifts 2.5. We're trying to push it a little bit higher, but we're still sort of limited, and I'll show you a longer time in a second. And the second point I want to show you is that if you break down, I kind of didn't explain the axis here. So this is the star formation rate as measured from the UV and the infrared. So they've accounted for how much light is coming out directly in the ultraviolet that's not obscured, and then adding it to how much that comes out in the infrared, because that should be the total. And so that's what's shown. I'm just picking one redshift interval here, redshift 2 to 2.5. So again, this is the average star formation rate of galaxies as a function of stellar mass. And this shaded region with the black stars is the average relation. And then in red and blue, I'm sorry, I should have labeled this. I had it on the previous version. In red, that's the portion of the star formation rate that's coming out in the infrared. And then in blue is the portion of the star formation rate that's coming out in the ultraviolet. So you can see at the highest mass galaxies, the ultraviolet component is tiny. Barely any of the stars, or barely any of those ultraviolet photons are making it out. They're getting absorbed by dust. As we move to lower masses, you get to a point in lower mass galaxies where they're maybe comparable. But you can see this is right about the point where our observations are starting to be limited. You can see the regions that are a little bit blurred out here. That's where our observations are no longer as complete, or we have to rely on stacking analysis instead of individual detection. So, really, if you want to be conservative, you would stop the plot here and say, okay, it looks like they're trending together, but we still don't know the complete picture there. Okay, so this is just at one epoch. So now if we then integrate back over all redshifts, or here I also have cosmic time, age of the universe. So this is sort of the big plot that we look at a lot of times. So this is the total star formation rate density, the total amount of star formation happening in a given volume of the universe at a given epoch. Okay, so in the local universe, I'll take a volume, I'll measure how many new stars are forming, and then I'll go to redshift 0.5 and 1 and 2, and I'll measure how much. And I've broken it down into the unobscured star formation directly from the UV photons from Hubble, and the dust-obscured star formation from infrared surveys. So what you can see, just like here for individual high-mass galaxies, the dust-obscured star formation dominates over much of cosmic time, all the way back to the universe was only about 3 billion years old. And then our infrared observations are lacking. And I'm going to talk about why that is in a second. We've been able to measure the unobscured UV photons all the way back to the earliest galaxies. And so the trick then is you can apply corrections to figure out how much dust you think is there. But really, ultimately, what you want to do is make this measurement and determine what the infrared obscured star formation rate density is. So the big question then is, why is our census of dust-obscured star formation incomplete? Why don't we reach out to this regime? So up until sort of currently, or recently, surveys of dusty galaxies, surveys at infrared wavelengths, have been limited to the most extreme galaxies. And this is demonstrated here. And we call these galaxies submillimeter galaxies because they were initially detected in submillimeter surveys. And so here is the original Hubble Deep Field from 1996, showing many hundreds of galaxies in this patch of the sky. And then here is the same region at 850 microns. Okay, and so you can see, you might not even know what you're looking at here. The white blobs are galaxies, or blended contribution light from galaxies. So this is showing the infrared light from star formation that's been absorbed by the dust and re-radiated in the infrared. And then here we're seeing the direct light in the UV. So you can see there's sort of maybe half a dozen detections in this map. And the spatial resolution is such that it's impossible to tell which optical galaxy it's coming from. So we're really just looking at the typical iceberg. So what's going on below here? How much infrared light is coming from all these other galaxies that we aren't picking out individually in this image here? So the challenges have been related to the observations. And at the most basic level, the resolution that you get on at a telescope depends on the wavelength of light that you're looking at and the size of your telescope. So if you're going to much longer wavelengths, so the optical sort of finishes around 1 microns, if I want to go to the infrared at 100 or 1,000 microns, that's several orders of magnitude. Then I'd have to build my telescope several orders of magnitude larger to match the resolution, which is not feasible. So the resolution that we typically get, here we've got sub-arc second resolution. We're resolving the light within individual galaxies. Here we've got 15 arc seconds. So, several galaxies can be blended within the same resolution element. That makes, as I said, identifying the source of light, which optical galaxy corresponds to this, very difficult. And it also fundamentally limits the depth that you can observe down to, right? You could integrate forever on this image, but you're never going to detect fact a small galaxy here that is behind this bright galaxy because it just gets blended. This is called confusion noise. So there's a fundamental limit to how deep you can go. The only way you can overcome this is by building a bigger telescope or using interferometry. The second challenge that's limited our progress over the years has been, since these galaxies have a large amount of dust, we see that a lot of the light is getting absorbed by dust. It also makes traditional methods of determining spectroscopic redshifts, which tells us where the galaxy is, challenging. Normally we would go and take an optical or a UV spectrum and determine where the lines are. This is a galaxy at redshift of 4 that's very dusty. You can't see any lines in this. There's a subtle break here, which is consistent with the redshift that we get from the molecular gas. So if you go to traditional methods of using the optical spectroscopy, it can be very difficult. But lately we've made a lot of progress using transitions of carbon monoxide, which trace the molecular gas, and those turn up in the radio and submillimeter regime. OK. So let me move to the LMT here. Sorry. That's a nice video. It's a good time to pause. So this is the Large Millimeter Telescope. This is the world's largest millimeter telescope, and I can now tell you that it is 50 meters. Greg was asking me during the cookies before, is it actually 50 meters now? And the reason is, when they were building this telescope, it was expensive, and they were filling in the panels, and they got to about 32.5 meters, and they ran out of money. And so the decision was made to create a secondary mirror to illuminate just the inner 32.5 meters and start taking data, show that the telescope works, and then finish up the rest of the panels later. And so we were able to do that. And the 50-meter dish has now been completed, and we'll be starting observations with it this winter. It's located down in Mexico at 15,000 feet, so it's an excellent site. It's comparable to Mauna Kea in Hawaii, where a lot of other telescopes are. It's owned jointly by UMass and the country of Mexico, so it's kind of an unusual collaboration. It's the largest science project Mexico has ever done, and it's just our institution currently. And so that has created some challenges along the way that led to some delays. We did this early science phase, as I mentioned. So when we had the 32-meter dish, we called that early science phase because we weren't operating with our full capabilities. And we had 2 instruments on there. So we had a 1-millimeter camera. So this was taking pictures of the universe at 1 millimeter, which is the infrared millimeter, submillimeter. So this is picking up the dust-obscured light from galaxies. And then we also have another camera that is a spectrometer that is called the Redshift Search Receiver because it measures these redshifted transitions of CO to tell you exactly where the galaxy is. It's an enormous surface, so it's actively controlled to keep its shape. The other interesting thing is we're partners in the Event Horizon Telescope, which is using a network of radio telescopes over the world to image the event horizon of the supermassive black hole at the center of our galaxy. So that's been sort of a cool side project that we've been able to be involved with. And just to put it in context for the astronomers that are used to thinking about ALMA, ALMA is a huge project, huge international project. Our single 50-meter dish has 1/3 the collecting area of ALMA. So the sensitivities will scale accordingly. And I'll show you later there's huge synergy between having large single dish telescopes and arrays of interferometer like ALMA. So here's an example of how LMT solves the first challenge I said, which is by going to a much larger dish. So even at 32.5 meters, previously the largest telescopes were 15 meters. So even at 32.5 meters, we had an 8.5 arc-second beam, and with 50 meters, we'll be at 5.5 arc-seconds. So for those who are, again, for the astronomers, this is comparable to MIPS 24 microns. So that, most of you can live with that, I think. So here's MIPS 24 micron. Here's a galaxy at 24 microns with MIPS. Then moving into Herschel. So Herschel was only a 3.5-meter space telescope. So it was lower resolution. You can see it had PACS and then also the Spire instrument. So the resolution here is 36 arc-seconds. So the pixel sizes are, much larger than the galaxy. Here's what we had at 1 millimeter with a much smaller millimeter telescope, and then here's now what we're getting with Aztec on the LMT. So comparable to MIPS 24 micron, really able to localize the source of the emission much better. And it also, in addition to giving you this higher resolution, it means that you can push that much deeper. Something faint that's over here, you can now detect that you would never have the hope of detecting over here. So it lowers the yeah?
Why are the images on MIPS and Aztec? It's not interferometry, so there's no beam, right? The beam's
Yeah, I mean, I don't know. This is just like an old postage stamp array that we have from an original proposal.
Okay.
This is a galaxy in a cluster, so it may actually have some structure to it. It may be a little merger or something. We should have the optical stamp beside it. That's a good point. Okay, so it lowers the fundamental limit that you can go down to. And this plot on the left here is the best way of demonstrating that. So what I'm showing is the limiting infrared luminosity, or you can also think of this as the limiting star formation rate that I can get down to as a function of redshift. So a galaxy at redshift 6, how faint of a galaxy can I see with this telescope? Galaxies in this dark shaded region are greater than 100 solar masses per year in star formation rate. Galaxies in this light shaded region are 10 to 100 solar masses per year. Our Milky Way is forming stars at a rate of 1 or 2 or 3 solar masses per year. Okay? So you can see the blue curves are showing what we could get with Herschel, the space telescope previously. And so you can see that those, you know, as soon as you get to redshift of 2, you're only looking at these extreme systems, as I showed you. But for the LMT, we're sitting, for the 32 meter, it's this solid curve here. So we're sitting down at something like 60 solar masses per year, which locally is quite high, but I showed you that the average star formation rate of a galaxy of a given mass gets higher at higher redshift. So this actually probes into a pretty normal regime. And then with the 50 meter, we'll be down here at sort of 10 or 20 solar masses per year. The other cool thing I wanted to point out is these curves are flat, right? So this is telling you that I can detect a dusty galaxy at redshift 2 down here at 10 solar masses per year equally likely than I can detect a galaxy here at redshift of 6. Normally, we think of light dimming as a function of distance, like a light bulb. You take a light bulb, you put it further away, you see less flux from it, right? It looks fainter. We experience this very neat thing at millimeter wavelength, which is called a negative K correction, where as the spectrum of light gets shifted, we're actually probing a brighter part of it. And that's demonstrated here. So again, I showed you these spectral energy distributions. This is optical light, infrared light. The millimeter is right here. So we're on the Rayleigh-Jeans tail of this, you know, Planck-like dust distribution. And as you redshift these galaxy spectra, you're moving them towards the right. And this stays fixed. So as you move it to the right, you're probing higher and higher up on this curve. So it dims, but you're also probing a brighter portion. And that's demonstrated here. So here is a galaxy at redshift 2 with the same luminosity. Here is a galaxy at redshift of 6. And you can see the flux that you measure at 1.1 millimeter is identical. Okay, so that's a really powerful technique because it means that we aren't biased to more nearby things. Okay. So this was sort of where we were at. I arrived at UMass 7 years ago, and we were operating with the 32 meters a few years after I got there. And I was like, okay, 60 solar masses per year, maybe we can do some stuff. But how can we go even fainter now? We always want to push the limits. And one way that you can do that is with gravitational lensing. So this is done across the electromagnetic spectrum. And if we want to study really, really faint galaxies, we target a foreground massive structure, like a galaxy cluster, looking for background galaxies that have been amplified and gravitationally lensed around them. So the background galaxy gets amplified and stretched as the light moves around this gravitational field, and the result is that we see a higher flux. So these end up acting like cosmic telescopes. As you have your telescope, and then you're basically sticking an additional telescope, you know, as the cluster to amplify the light even more. And here's a nearby galaxy cluster where you can see all these sort of stretched out blue bits of light are background galaxies that have been amplified and distorted around this galaxy cluster. So a couple of years ago, the Hubble Space Telescope was thinking, okay, we have, you know, another 5-ish years until the James Webb Space Telescope launches, and it's going to have a limited lifetime. It's only going to live for about 10 years, and so we have to really optimize the science that we do with James Webb. This is a huge, you know, a hugely expensive project. So what can we do now with Hubble that will help us learn about what we can do with James Webb Space Telescope? And the plan that the committee came up with was spend a lot of time, and this was 1,000 orbits of Hubble time. This is like $6.5 million in operations. They would spend 1,000 orbits integrating very deeply on 6 low redshift clusters to study the background galaxies, because the background galaxies that will be lensed, that you can see with Hubble, might be comparable to the galaxies that we will then individually detect without lensing with JWST. And so we can start to learn about these systems. So Hubble spent 1,000 hours, Spitzer, everything else then followed suit because that's how it works in astronomy. And the big thing is that anytime you have this gravitational lensing, you want to know when you make your measurement, okay, how much it's been amplified for. And that requires very detailed modeling of the mass structure to determine what the magnifications are. And so as part of this program, they solicited several groups from the community to release public magnification maps so that if I know the distance to my galaxy and where it is, I can look up what the magnification is. I don't have to be an expert in the modeling to extract some science. So we did a program with the Large Millimeter Telescope of the frontier fields. We looked at 2 of these clusters, and it was a modest program. We spent 20 hours on each of them, and reaching these depths in millijanskis. I'll show you what they are in fundamental units later. It was a big team. We collaborate really nicely between the Mexican side and the UMass side because we've realized that we should maximize the high priority science and work on things together. So what I'm showing here is the individual dusty galaxies that we detected in our Frontier Fields program as the blue dots overplotted on these magnification maps. So this is not an actual image, right? These contours in the background, this black image, and then the red contours are showing the magnification, so how much the galaxy's light is being amplified by. And then the blue circles are where our millimeter sources lie. So these are where the dusty galaxies are. And you can see a lot of them are sort of near the outskirts where we have lowish amplifications of 10, 20%, something like that. It's still nothing. But we have a couple that are close to these high magnification areas up to magnifications of about 10. So that's really exciting because if you'll already making very deep observations, you find a faint galaxy and then you determine that it's been amplified already by a factor of 10, you're pushing much deeper than you were ever able to look at before. So I'm going to tell you about this one galaxy here, and then I'll tell you a little bit more about the rest of the sample. So what we found was in the previous image here, I showed all of these nice arcs. And the other result of gravitational lensing is you often get multiple images of the same background galaxy depending on the geometry. So you'll get one image of the galaxy here and one image of the galaxy here. And the multiple images can be really powerful because they really help you understand the mass structure. And they also help you determine the properties of the galaxy because you're taking 2 pictures of the same thing, but you've got an independent observation. So what we found was that one of these sources, this one here, one of these dusty galaxies, was a multiply imaged galaxy. So here's a zoom in on the 3 images. There, I've got them. So this is the whole cluster, and then there's image G. 2, 1, 3. So there's 3 images of the same galaxy. This was already known from Hubble. So the people who had looked at the Hubble images, determined redshifts and everything, had already published this as a known multiply imaged system. And we detected the brightest, the component with the highest magnification here with the LMT, with Aztec. And our limits on these other ones are completely consistent with the flux that we expected. So here it is zoomed in now with the actual observation. So in the background is the Hubble image, and then in green are the 2 known components of this multiply imaged source, and then the red contours are from our Aztec 1.1 millimeter imaging. So this is the light from the dust. This is the dust emission. And you can see we're detecting 2 of the 3 components, and the other one we have a limit on, and it was completely consistent. This galaxy lies above a redshift of 4 at a time when the universe was only 1.5 billion years old. Okay? Now this is in the realm where we don't really know what's happening with the overall amount of dust-obscured star formation, and it's also close enough to the beginning of universe where we have to start thinking about how much time do we need to build up dust in galaxies, because at the beginning of galaxy formation they were all made of hydrogen, and so over time the metals were created, the metals that are in dust were created, so you need to have a little bit of time, so expect that there is some ramp up in this over time. So this was quite interesting that we found quite a lot of dust emission in this galaxy quite early on. So I'm saying in the title here that this is a normal galaxy, not an extreme galaxy, and I just want to demonstrate that to you here by putting it on this plot that I showed you earlier, which is the star formation rate as a function of stellar mass. The shaded region is the average relation for redshift of 4. And the blue points are a couple of observations that were made with ALMA on earlier 2 years ago in 2015. And then we've got our galaxy is plotted at 2 different redshifts. So this is the challenging thing about this system is it's known to be a multiply imaged source, but it doesn't have a spectroscopic redshift. So we've got 2 solutions for the redshift from the different lens models. So it's either a redshift 4.1 or 4.3. So we've plotted it at both of these redshifts on all of these plots, regardless of the redshift, right? 4.1, 4.3, I don't care. It's above redshift 4. I want the redshift eventually. But this is a very dusty galaxy at very early times, and it's relatively low mass. So, it's down around 10 to the 10 in stellar mass. These black solid symbols are sort of where we really know what's going on in this sequence. And then again, this is extrapolation when you're incomplete. And then the other thing that's plotted here is the star is the total amount of star formation, and then the square is how much is coming out in the infrared, and the diamond is how much is coming out in the UV from the Hubble imaging. So again, a very small amount of the star formation is being traced directly in the ultraviolet, and you really need the infrared to make full senses of star formation in this galaxy. Okay, so there you go. 80% of the star formation in this relatively low mass galaxy is obscured. And that may be surprising at this epoch. So I'll look at that in a couple of other ways. The first way I wanted to show you is this is another plot showing what fraction of star formation is obscured by dust as a function of stellar mass of the galaxy. Okay, so I've showed you there's a nice relationship between star formation rate and stellar mass, and I also showed you that the highest mass galaxies are most obscured. So now this plots sort of that obscured fraction as a function of stellar mass. Okay, so you can see this is this star formation coming out in the infrared versus the total, the ultraviolet plus the infrared. So obscured fraction. So if you're up here, a lot of the light is getting absorbed by the dust. If you're down here, a lot of it's getting out in the UV. And this is a function of stellar mass. And you can see, I'm not going to go through all these curves in the dashed line right now, so just focus on the main relation here in black. There's sort of a nice tight relation, and it doesn't seem to matter what redshift or what epoch these galaxies are at. The relationship between how much is obscured as a function of stellar mass is actually the same. So that's what's shown by these colored points. All the colored points pretty much follow the same relationship, which is kind of maybe counterintuitive given that I told you that the higher redshift galaxies have much higher star formation rates for their stellar mass. You may have expected there to be a difference in how much came out in the obscured versus unobscured phases. Okay, so this stops at redshift 2.5. If we plot our galaxy at redshift 4 on there, it's right here, not inconsistent with the relationship. So, again, this is just one galaxy, so we're not going to claim anything, but it kind of shows that you can have these very obscured galaxies back at quite early times. Another way of looking at that, this is now I'm showing the ratio of the infrared star formation rate to the UV star formation rate. So here it was infrared over UV plus infrared. Now it's just infrared over UV. So just another way of looking at it. If you're up here, you have a lot of infrared relative to UV. If you're down here, you don't. So here's star formation rate ratio on this axis versus this quantity beta, which is the slope in the ultraviolet portion of the spectrum. Now, the reason why this graph is so interesting to look at is in the absence of deep infrared observations, in order to determine the total star formation rate of a galaxy, people have often just observed the UV, and then they've determined the slope in the UV, and then they've gone up to this black curve, and then they've said, okay, this is where I am because I have to be on this black curve, and then they've determined how much is coming out in the dust up. So they've indirectly kind of inferred this. So what is this black curve and what makes it so special? This is a relation that's been established for local starburst galaxies. And many other populations of galaxies have been analyzed even out to redshifts 2 and 3, and they've been found to lie pretty consistent with this relationship. So it looked like the ultraviolet slope would be a good proxy for this dust obscuration. But it breaks down in certain situations, and one situation where it breaks down is if you go to lower metallicity. So you've probably heard before, anything that's not hydrogen and helium is a metal to astronomers, and we expect to have lower metals at earlier times in the universe because it takes time for them to build up. So this dotted curve is the relationship between the infrared and UV as a function of UV slope for the SMC, which is a lower metallicity system. So if you have less metals, you have less dust, so less dust catches your photons, so you get more UV out relative to your infrared. That makes sense. And observations have been showing, observations that have started detecting individual galaxy in their dust emission have been finding lower ratios, more consistent with this SMC curve. So this might be indicating that these systems have lower metallicity. But there's many other things that can be affecting this, such as geometry of where the infrared and the UV are relative to one another. I don't want to get into all of that here, but I just wanted to make the point that this is sort of counterintuitive, this galaxy that seems to be in this region where we're inferring lower amounts of metals, less dust, but yet we found that 80% of the star formation is obscured by dust. Those are kind of, not completely consistent with one another. A recent paper said, well, this beta is maybe not the best quantity because there's all these other systematics. So what if we just plot stellar mass on this axis? So, So the y-axis here is the same for these two plots, but the x-axis is going from UV slope to just stellar mass. And we found stellar mass seems to be a pretty fundamental quantity. And this paper found that out to about a redshift 2.5, most observations lay on the same sort of sequence. So there wasn't much evolution. And even when you went down to lower stellar masses, where presumably you had lower metallicity. So if we plot our galaxy at redshift 4 on this plot, it is slightly lower. Again, this was established for redshift 2.5. So we're still finding that we're sort of deficient in the infrared relative to the UV for the size of galaxy that we are, okay? Even though we still have 80% of the star formation that's obscured. Okay, so here's the plot I showed you before, which is the limiting depth that you can get to. So, 10 solar masses per year, 100 solar masses per year for different surveys. The red curves is a function of redshift. Here's where this new galaxy lies. It lies below even the limits for the 50-meter LMT. So that's really exciting. We're probing a new parameter space. But this is just one galaxy, right? And so, you really want to look at much larger samples. So we're still working on the analysis for this. But we've got we had 25 detections in our full survey from this frontier field survey. These are showing the K-band images. I'm sorry, I'll blow these up in a second, but these are the K-band images. So that's optical light tracing stellar mass 1 micron, with the contours from the LMT over top as red. And again, I'm going to zoom in. I just wanted to show that we have them for all of them here. So those were taken with ALMT, and since we've taken observations with ALMA, because even with the LMT at 32.5 meter, we still have that 8.5 arc-second beam, and it isn't exactly clear which optical galaxy you would choose. There's a couple examples here. Let me show you here zoomed in. So here's two examples. Ignore the bottom for a second. Here's two examples of two different galaxies. The red are the contours from the dust emission. The background image is optical light. So you can see there's a faint galaxy here, another one here. They're all sort of equally distant from the middle. They could be contributing to the dust emission. Again, here you've got something faint here, and then something brighter over here, right? So you can't figure out exactly what's causing the dust emission from these images up here. So here on the bottom, these two panels are images taken with ALMA, the Atacama Large Millimeter Array. This is an interferometer at millimeter wavelength, so it overcomes these issues to do with resolution. We've gotten resolutions of about an arc-second, comparable resolutions to some of our optical data. And you can see now, so this galaxy here is the one that's lighting up at millimeter wavelength. So these red contours are the exact same wavelength light as this image on the background now. And we've basically localize that light to be coming from this galaxy. Just let me do this one first. And then this is the same thing here. This faint guy underneath here is the one that lights up in the millimeter, not this one that was brighter in the K-band. Question?
So it seems when doing like the cross IDs and stuff, the fact that there's these significant offsets between the ALMA data, the ALMA source, and the centroid of the LMT light. So is this because of astrometric uncertainties, or is there another source? I'm wondering why this obviously down in ALMA source is not centered in the LMT beam when there's not much confusion from other millimeter emitters.
So on average, the offsets are consistent with 0. Well, I'm just showing two examples where they're offset to the north. It's just the uncertainty, and it's not that big, right? This is 2 arc-seconds here, roughly. So and the beam is 8.5 arc-seconds. So it's totally fair game to be 2 arc-seconds in an 8 arc-second beam.
That was 10 arc-seconds.
Yeah, but I gave you, I'm giving you two examples where they're shifted in the same direction, so it makes it look like there's an astrometry issue. But on average, if you plot sort of delta position from from ALMA and LMT. They're just scattered around 0 with a distribution as expected. Yeah. And that's an important question because we want to understand that, because obviously we cannot get ALMA imaging. Once we survey huge fields with the LMT, we're not going to get ALMA imaging for everything. So we have to understand this well enough to make, to develop these techniques. So this really demonstrates the great synergy between a big single dish telescope like the LMT that's relatively inexpensive to go and point at a region of the sky. It finds the bright sources, and then you go with ALMA and localize the emission. To survey the region that we did with the frontier fields with ALMA would be like 500 hours or something like that. There's no way that project would ever get done. And so you can do it inexpensive with the LMT, find the sources, and then follow them up with ALMA. Okay, so in the last couple of minutes, I just wanted to touch on the second challenge, which is determining the redshifts, or distance, to these dusty galaxies. And the other instrument we have on the LMT is the Redshift Search Receiver, which has an instantaneous bandwidth, a very wide bandwidth. So that basically gives you a wide range where you can detect the carbon monoxide transitions from the molecular gas. In addition to getting the instantaneous bandwidth all at once, you also get 100 kilometers per second resolution. So these two things in other instrumentations don't go hand in hand. Often if you have a wide bandwidth, you get 500 kilometers per second resolution or something worse, or you go for a smaller band for better resolution. So this is a really well optimized instrument. This shows nearby galaxies, and this shows the rich array of lines that you find in some nearby galaxies over this range. And this plot here shows over the range that we have in frequency where certain CO transitions lie as a function of redshift. And the regions in blue and green are showing you where you would detect 1 or 2 carbon monoxide lines simultaneously. So in all the region where you detect at least 2 lines, you get an unambiguous redshift right away, because you see 2 lines and they're separated by the difference in frequencies with the 1 plus z term. So this is a really powerful instrument for determining where the galaxy is once you find it, and it's probing the molecular gas, which goes hand in hand with the dust, right? Gas and dust trace one another, and so this is a really great tracer. So here are some observations that we've taken with the Redshift Search Receiver of distant galaxies. Here's the redshift, 1.3, going all the way up to 4.7, and you can see the little spectra with the lines popping in. So here's the CO 2 to 1, 3 to 2, 3 to 2, 4 to 3, and the 5 to 4 line. Okay, so you take this large spectrum and you can determine the distance to the galaxy. And these are 30-minute integration times. These are super short to do. These are quite bright galaxies, but with the 50 meter, we'll have larger apertures. So we can do this on more typical galaxies. And I wanted to demonstrate that you get these peaks which tell you where the redshift is, but if you zoom in, you also get a nice structure and profile for the line so that you can measure a molecular mass. You need to be able to resolve the line over multiple channels to be able to integrate and determine the molecular gas mass. So that's another thing you can get from the same observations. So with my last couple minutes, I'm just going to talk about what we're doing next. So I told you that we are now 50 meters, and so we're going to be operating with resolution of 5.5 arc seconds resolution. But we have grown out of our instrumentation. Our instrumentation that we currently have was built over a decade ago. So the next big thing is a new camera. And before I get to that, I'll just demonstrate the power of the resolution. So this is a simulation where I've taken the same galaxies, given them some brightness in the millimeter wavelengths. I'm looking at the same wavelength in both panels, but this is simulated with the LMT5 arc second beam, and this is with sort of typical submillimeter beams that you would have with Herschel or Leboka or some other telescope. So you can see, there's 2 bright sources here, and they just get, they oversaturate the image here such that all these other fainter things around you have no hope of seeing, right? And so you can see the depth. You can just see by eye the depth that you're going to get down to in these types of images. To quantify that a little bit more, I'm going to show this in a slightly different way. So I was showing the luminosity limit before as a function of redshift. Now I'm showing you the infrared luminosity limit as a function of survey area. The larger part of the sky that you look at, the better statistics you get on galaxies, right? We're used to doing these pencil beam surveys with Hubble, but really you want to look at much larger patches of the sky. Again, this is the limit for 100 solar masses per year in star formation. This is 10 solar masses down here. The colored symbols are all previous millimeter, submillimeter infrared telescopes. So for the large area surveys of 100 or 1,000 square degrees, they've been limited to very, very bright galaxies, 1,000 solar masses per year, just completely extreme systems. And the deeper surveys have all been limited to very small areas. The ones in dashed here actually haven't been completed yet. So, you know, they should just erase those because those haven't happened. So this is at redshift 2.5. Here's what we're going to do with the LMT and our new instrument called Toltec. So we were funded to build this instrument a year ago. It's a 5-year NSF-funded project where the first 3 years we build it, and then, or the first 2.5 years we build it, and then we do some legacy surveys, which are all publicly available to the community, and which we've currently begun discussions to determine what fields we should observe. Nominally, we've determined that we're going to do 2 extragalactic, so galaxy evolution surveys, one that's sort of a largish area, like 100 square degrees down to this limit, and one that's a smaller survey, 1 square degree down to the 10 solar mass per year limit here. But, you know, so the delta on the exact depth and area, we're still trading that off along with deciding which actual fields we're going to point at. So this is definitely probing new parameter space and giving us excellent statistics in these dusty galaxies. Here's just some statistics on this camera. Before I was talking just about 1.1 millimeters. We're actually doing 3 wavelengths simultaneously with Toltec, so 1.1, 1.4, and 2.1. And that's so that we can actually measure the Sunyaev-Zeldovich effect to search for distant galaxy clusters as well. So that's sort of another thing you kind of get for free with these surveys. The beam size, 5 arc seconds at 1 millimeter, and just some map technical specs here. So we've begun building this telescope, and we've begun defining these surveys. So there's 2 surveys that are sort of galactic surveys, and then there's 2 extragalactic ones. We're defining the survey with input from the community, and we're going to make all of the data products public. So we're sort of networking with the community now. So for the astronomers or even the physicists, if you feel compelled to switch fields, you can sign up on our website and join these surveys. And if you know that you really want to do this 100 square degree survey in this field because the ancillary data is fantastic, we want to hear about that. Okay, so in summary, I hope I've convinced you that big single-dish telescopes like the Large Millimeter Telescope are really important for completing our census of cosmic star formation. With the Frontier Fields program that I showed you, we detected galaxies much fainter than you could with previous submillimeter surveys. We detected this multiply imaged galaxy at redshift greater than 4 that maybe has low metallicity, but 80% of its star formation is obscured. It's relatively low mass. We're trying to follow this up with more observations to really pin down what's going on, if we can measure the metallicity. The ALMA follow-up is ongoing, but it allows us to localize the emission so then we can go and exploit the multi-wavelength data to get better statistics on the dust-obscured star formation. And with these future surveys on the 50-meter and Toltec, we're going to detect dust in tens of thousands of galaxies to sort of complete the census of dust-obscured star formation. So I'll stop there.
Thanks, Alex. So we have time for some questions. Okay, I've got one. Oh, Hume, did you have? Go.
You showed the integrated photon from the very beginning.
Yeah.
You had these numbers, but I didn't really understand that maybe. So what is this 23, 24, 960?
That's the integrated power under each of these distributions.
In these units?
Probably not, no. I'm sure it's been normalized by some. I'd have to look back at the paper and see what it is. But it's basically integrating the light to determine how much total light would be under the optical versus the infrared. And they're comparable, with obviously much more coming out in the cosmic microwave background. But there's no information about galaxy formation and evolution over here. So, yeah.
While you're on that plot, could you just say a few words about why the Hubble structure that has new sources?
Yeah.
On the way, or
Yeah.
the way it goes?
No, yeah, so this is, so at the most basic level, if you just go here and you look at the shape of individual galaxies, and then you redshift them because they're going to be shifted, right? So these galaxies are all shown at redshift of 0. But this plot here includes light from galaxies at redshift 0, 1, 2, 3, all added up together. So let's say, let's just say for the purposes of this argument, you only have galaxies like this red spectrum. So you're adding up a whole bunch of these, but a whole bunch of these shifted from one another as well, right? So it sort of broadens both of these peaks. But it also, the fact that you still have, so it broadens the peaks, it stretches this out so that the slope of this side is shallower than it is for any, than it is for any individual galaxy. So that's one indication that more of the light down here is coming from more distant galaxies. We know from this other plot here that most of the star formation is happening during this peak epoch around redshifts 1 to 3. So we know that most galaxies are shifted by that amount, 1 plus z. And so most of the shape that's going on here is just from the, adding up the integrated light from individual galaxies. There are some other factors that go into it, gamma ray absorption in the mid-infrared, but I'm not an expert in that. But there's some measurements in here that help with that. Yeah. Does that answer your question? Yeah.
So you had this plot from your work with Kate on the mass trend of the obscuration.
Yeah.
And it seemed constant for pretty much all redshifts.
Yeah.
What's driving that? Is it metallicity that drives that?
Yeah.
Is it like a mode of star formation that drives that?
Yeah. So we were surprised initially because, so as you go to more distant galaxies, we know that for a given stellar mass, they have higher rates of star formation. But we also know that they're smaller, right? Because there's a size evolution. So the sort of arguments that we discuss in the paper is that, those two things are maybe conspiring together to keep any evolution that you would, because if you just took a galaxy of the same size and scaled up its star formation, you would change this obscuration, right? Because if you just add more star formation to an existing system, it's just more obscured because, there's more dust generated and all of that.
But it'll be at higher redshifts, so it'll be lower metallicity too.
True. I don't know that we're really getting down. Maybe down here, but up here, I don't know that there's a lot. We do that argument as well. So in the appendix, we look at the metallicity evolution and see how much that could make a difference. And we find that doesn't make a big deal, at least up here. The other thing that, like a lot of this stuff, the IRX beta, everything sweeps under the rug is geometry. Right? So in discussing all of this, you just think about a very basic system of stars forming and then dust around them, and the photons travel out, and some of them make it through the dust, and some of them get absorbed and re-radiated. But that's sort of like a very idealized situation. Really what you have is patchy regions within a galaxy where stars are forming, and then you also have interstellar dust throughout. So some regions, the photons may get out easier. So you may have a lot of UV light coming out from this side of the galaxy, and a lot of infrared coming out over here, just depending on how the regions are distributed, in which case it doesn't make sense to compare the infrared, like on an IRX beta plot. That doesn't make any sense, right? The UV slope should not be related to it. So I show these plots of IRX beta, but I'm not a fan of it. I don't think it's a helpful process because I think geometry is a big one as well. So the ideas we discuss in Kate's paper, to get back to your question, is that perhaps the increase in star formation and the size evolution sort of conspire together to make it look like there's no evolution as a function of stellar mass. Because if you look with star formation rate on this axis, there is different curves, right? That's in the paper as well. Yeah.
I have one more question, which is, you have these deep ALMA data on the frontier fields.
Yes.
Are you looking at all at the infrared emission of the cluster members?
Yeah, so not yet, but we could.
2 arc-second beams, right? So.
Oh, for the ALMA?
No, well, LMT is, what's the beam size for the 50 meter again?
So the data that I showed was taken with the 32 meter, because that was taken a couple years ago. So that's 8.5 arc seconds.
Okay, that gets hard.
So that gets hard in the cluster center. But we've got our ALMA stamps, right? The ALMA field of view is bigger than what I'm showing.
Right.
So we were planning on doing, in addition to finding the main source, looking at the other galaxies that pop up in our ALMA images and trying to do some science with that. So we just got the ALMA data recently, so we're still working through that. But yeah, but unfortunately, like many of our sources are not near the center, right? Like, you know, this is the high magnification areas here. This is sort of the cluster core. I should have a scale on here, right? But many of our detections are out here.
That kind of makes sense because the cluster core is super dense, so it's probably mostly passive. Right?
No, but in terms of like, these are mostly all going to be background galaxies at this limit.
I see what you're saying.
Yeah,
Okay.
and so the fact that they're avoiding the high magnification region, this is, we've simulated this and this is what you expect to see, but it's just like when you initially say, and this is why actually, so I don't know if you know, Franz Bauer did this survey with ALMA of just the central region with ALMA and spent all this time and barely detected anything. And that's because you can see here, if I just did a deep survey here, I would see one thing, right? Because many of them, you know, the effect of lensing spreads stuff out because it gets pushed away from the center. But yeah, but we have ALMA stamps in all these places. So we have ALMA stamps at different virial radii from the center, and we could look at the cluster galaxies within those regions.
But you're not detecting any sources near the center of the cluster, projected or not. Those
No.
are all your sources.
The closest
Yeah.
one is this
So there's
strong lensed
no
one.
strong emitters in the cores of the. That are
No. Yeah, so here's the core of the cluster, and
Right.
here's the multiply image.
So it's
That's the
all
closest one, yeah.
Okay.
Yeah.
Thanks. Okay, well, let's thank Alex again.
Thanks.